Hello everybody, today we'll be going over the physical properties of a few different materials, but before we do that, one of the main components of figuring out those properties is knowing how to plot them on the stress strain curve and what those plots mean. So the first part we'll be going over is elastic deformation, which is from right here to right here, and what it is, it's the amount of force that a material can take while still retaining all of its original strength properties. So if we apply force X to here and then let it go right up here, once we do that, all of the original properties will still be retained for that material. Now, second thing we're going to go over is yield strength. So yield strength is this point right here, and in some graphs it might differ, but we'll also go over that. And what it is it's that ultimate final strength, those shown right there. It's that ultimate final strength that we can apply to a material before it starts losing its properties. We'll go over that, which is plastic deformation.
Plastic deformation is the nonlinear curve we have between the yield point and necking. It represents the stress in relation to strain that the material will experience before it begins to neck.
So then we'd reach necking. What happens in necking is in the middle of the material will end up stretching out, and then it's an exponential downfall in stress, and then not much shorter in the strain. We'll see the end of the experiment. So if we take a look here, we have the 4 graphs of pure aluminum, 768 aluminum, pure magnesium, and Az63. Az63 is just the alloy of magnesium that contains 6% aluminum, 3% zinc. And so we can see that the aluminums will have a less defined yield point as compared to the magnesiums. However, they're all, for the most part, the same shape. So how precisely do we find it? Well, in this situation, what we'll do is we'll determine the slope using the change in stress over the change in strain, where the data points will come from the elastic region, which we defined as the linear line in the stress strain curve. So what we'll end up doing to find the elastic modulus is we'll use a formula E equals stress divided by strain, where we'll pick 2 points from the elastic region, and then we'll plug those in, and I'll show you in just a second how that relates to what we had previously on our graphs. So now that we have the main formula down, what we'll go over real quick is the actual calculations we made. So as you can see up on the top, we have all the elastic modulus formulas and data points put in. And as you can tell, one of them is a bit different, and that is 768 aluminum. And the reason that one is a bit different is because we're measuring in MSI. And the reason for that being is because the data points for the linear part of the curve weren't available online for this specific alloy. So we had to kind of make do with what we had and use the MSI calculation. But all in all, we were able to achieve all of the different elastic modulus measurements for the 4 alloys. So relating everything back, the entire curve is able to be plotted due to tensile strength. One of the most common tests done to calculate it is using the TTM. At the end of this, we'll show you a video demonstrating the process. And another term we can use to define it is UTS. So that's ultimate tensile strength. This is essentially just another term for the ultimate yield point, as it defines the load a material can undergo before becoming 100% unrecoverable.
And you can start to see the necking.
So establishing a yield point, which is a point at which a material's behavior transitions from elastic to plastic, is easier in some materials as compared to others. Some materials will not have a clear yield point, so what we will do to establish one is we'll draw a parallel line starting at the point of usually 0.2% of strain, and then where the line intersects, that's our yield strength. Materials like aluminum and its alloys often have to have that yield strength calculated like that. So as we can see, right up here would be our usual calculation of one, and right there is the aluminum, is the way we calculated the aluminum one. So just a quick little representation of the data. Aluminum was 40 MPa, 768L was 683, and so on. So ductility can be defined as the ability of a material to undergo plastic deformation until it fractures. And so we use the percent elongation and percent reduction formulas to calculate the ductility. So we see percent elongation is length final minus length initial over length initial times 100%. And from that, we can deduce what RA means. And if we look at the data, we see that AL, so aluminum, has 35 to 40% being the highest. That being because it is one of the most stretchable metals to say. Magnesium is much lower, and so 76 8AL, they're coming in all under 10%. So ductile materials undergo significant plastic deformation before breaking, while brittle materials undergo virtually no plastic deformation before breaking. And I'll be showing you a video right now to give you a demonstration of this.
We can see in the video that the ceramic, the glass bottle, shatters immediately upon impact, showing essentially no ductility, while the metal lid has a noticeable indent in it.
Definition of resilience is the ability of a material to absorb energy when it is deformed elastically and release that energy upon unloading, or we can call that energy break. Units are joules, meters to the negative third, or pascals. In this case, we'll use megapascals because that's generally what stress is given in. The formula for resilience is equal to the integral from 0 to the yield strain of stress. Another formula we can use is the resilience is equal to sigma y epsilon y over 2. That is used in a linear relationship, which is going to be used in this example. So given this strain and stress curve of aluminum 6061, this is just a general form of aluminum. There's many different aluminum forms, but in this case, we will use this one. So first you will locate the linear relationship in the elastic region. Then you will find the yield point, and then find the area. Using 1 and 2, we can do 3. So UR equals 1/2 times 240 times 0.0034, 240 being the yield point and 0.0034 being the elastic region strain, which can be defined as 240 divided by 70,000 megapascals. So given that, UR equals 0.41. Toughness is defined as the ability of a material to absorb energy and plastically deform without fracturing. Units are the same as resilience. And toughness can be found by finding the area under the curve of the whole stress strain curve. So this time we'll do the whole area, not just the elastic region. So going back to our previous example, first we want to find resilience, which we did already in our previous example. Then we'll find the area under this rectangular region and then this triangle region. Doing this, the rectangular region is just equal to the yield point times the difference of the yield strain and this distance, which is here. And same for the plastic region, except this time our yield point for the triangle is 70. So overall, the toughness is 4.97 megapascals. You can do this for all given graphs of any material, and that's it.
If we put a tensile load of 4 kilonewtons on a pure aluminum and pure magnesium cylinder, how would we find the change in length and width? Using the given values of length, diameter, tensile force, and the modulus of each metal, we will first calculate the tensile stress, using the tensile force and the cross-sectional area of the cylinders. Both metals will undergo a tensile stress of 127,320 pascals. Next, we will use that and the modulus of the metal to calculate the strain. The strain of aluminum is 1.8 times 10 to the negative 6. We will use this number to calculate the change in length. Using Poisson's ratio, we will calculate the lateral strain, which gives us negative 6.09 times 10 to the negative 7. This will be used to calculate the change in width. To calculate the change in length, you multiply the original length by the strain. And to calculate the change in width, you multiply the original width by the lateral strain. Under the tensile force, aluminum will lengthen by 0.0018 millimeters, and the diameter will shrink by 0.000121 millimeters. And magnesium will lengthen by 0.282 centimeters, and the diameter will shrink by 0.019 centimeters.